This meeting. We are good. All right. So in the last class, we talked about the basics of HSPICE and looked at some options that HSPICE provides, some basic coding strategy. For example, how do you define voltage sources and current sources? And we'll see more of that as demo codes today. And remember, I kept referring to the HSPICE user manual, which I've also uploaded on Canvas. I highly recommend download it, keep it handy. You may not need it now, but in some point in the future, you might need it. So just refer to that chapters that I'm mentioning. It happens to me all the time. I mean, if I code after 6 months, I forget what was the sequence of writing. Pulse is fine, PWL is fine, but there are other types of voltage, stimulus that we can create in HSPICE. I don't remember the syntax for everything. Every time I need it, I just go back to chapter 9 and see all the list. Just copy paste from there. So moving forward, we discussed the types of sweeps. That's where we stopped, I think, in the last class. Yes. So that's how you sweep different parameters in HSPICE. And basically, I'll be drawing parallels with cadence simulations that many of you have done or are doing right now for your research. So for example, in cadence parametric sweep option, you can choose the start and stop value of a parameter, and then you can choose the step size. You can also do nested sweep, parameter sweep within parameter sweep. You do all that in SPICE. The good thing is, like, you just have to write a line of code instead of selecting. This is good or bad for some people. For some people it is good. I will tell you why this is very powerful when you do it in code, because you can parameterize each one of them, and you can basically, without going to the graphical interface every time and changing them manually, you can write a code that automatically changes it. And it becomes extremely powerful when you use alter. Remember I told you about alter? You can just keep altering the conditions of the simulation as many times as you want. There is no limit. And that way, this becomes very powerful when you want the computer to work while you're not in front of it. So just submit a really big set of command with multiple alters, and when you get back, you see a lot of results. The more you automate, the more optimization is possible. By the way, for DC simulation, you start with .dc. .transient, you start with .tran, not full transient. .ac, that's also an option. And then whatever variable you want to vary, for example, let's take a look at this particular example. You are changing the input voltage, which is marked as V in. You're going from start value, and that's how it is mentioned in the user manual. When you see that user manual, okay? Basically, you start from 0.25 volt, stop at 5 volt with steps of 0.25 volt, as simple as that. And you learn it from the user manual, okay? Basically, what the second line shows you is that you can vary multiple parameters. So you're varying VDS from 0 to 10 with this step. And then you are varying VGS from 0 to 5 with these steps. As simple as that. You're varying so the way it does is, it takes one VDS and sweeps VGS entirely. And then it moves to the next VDS point and sweeps VGS accordingly. So there is a set of numbers you get, huge chunk of data. You can prune them accordingly. Transient is pretty similar. You start with .tran, and by the way, notice you start with say 10 nanosecond to 1 microsecond. Okay, so you just have to provide basically, sometimes you can provide, this is actually the step size. The first one is the step size, and the next one is where you stop. Typically it always starts with 0. This is your step size, this is your stop. UIC stands for use initial condition, because in transient, when you start at time equal to 0, you don't know where the system was. So you have to provide some initial condition if necessary. Sometimes if you don't provide anything, it will assume something and go from it. But for most simulation, we try to provide initial condition. So that's why it says UIC. Okay. In many codes, you will not even use it because it is understood. It is basically the default. It will use the initial condition if there is one. Okay. And then, by the way, within the transient simulation, you can sweep something. For this example, you're sweeping the temperature. Okay, as simple as that. So you can nest DC sweep within a transient analysis. And these are just representative samples. There are many other options that the user manual will give you. One particular very useful example is the type of sweep you can do. This is decade sweep, linear. So all these examples that you have seen, these are linear sweep, meaning you go from 0 to 10. I hope you can see my cursor, right? Yeah. You go from 0 to 10 in steps of 0.5 and you do it linearly. So you haven't mentioned anything, but it automatically takes linear because that is the default. The user manual will tell you what's the default option. But imagine you want to do a decade sweep. Decade sweep is similar to logarithmic sweep, by the way. You go from 0, 10, 100, 1,000. If you want to explore a long range of numbers, and if you do linear sweep, it's probably going to take a while and also difficult to handle the data. You can do a linear sweep, of course, but you'll see how quickly the data piles up. I remember, I mean, I can tell you how many times I kind of maxed out the space allocation for a server by doing so, because the numbers can easily add up. But if you don't want, first, typically what we do is we can do a decade sweep and focus on the range that appears to be useful. For example, from 100 to 1,000, you see most interesting results. So then you can go to 100, and from 100 to 1,000, you can do a linear sweep instead of doing a linear sweep from 1, which will be like significantly more numbers. Okay, so the way you do it is, notice, you start with .dc, you can define the parameter name, whatever the parameter is, then you mention the type of sweep you want to do. If you want to do a decade sweep, mention decade. If you want to do a linear sweep, you don't even have to mention anything, but you can mention, it doesn't matter. And then these are the start stop numbers and whatnot. And don't worry about sweep Monte for now. I will show you what that means, in one of the upcoming slides. So Monte Carlo simulation is something that we definitely want to focus on in this course. So for now, just ignore this part. And remember, temp is a keyword that is reserved for temperature. You cannot use it. It cannot be used as a name for any other variables, just so you know. That's why I'm showing it here separately. Oh, by the way, this is an interesting, the reason I chose these ones for you is because at some point in my career, I needed to use them for one thing or the other. So when you do DC sweep for example, temperature, you can do a point of interest sweep instead of a DC linear decade sweep or something like that. So POI is point of interest. I want to do it for like these few values. Okay, so you can do it. All right. So something that we'll see in the demo as well is how to incorporate external models. And I told you that HSPICE is very powerful because it allows you to incorporate external model. So this is one source of external model that I will be using, and I think you can also use for your project, which I will post about after today's deadline. I will talk about and provide the detail of all the plans I have about your project. And by the way, these models are developed based on the ITRS data. You know what ITRS is? This is what it stands for, International Technology Roadmap for Semiconductors. It is basically a set of numbers that everybody agrees upon. So for example, companies like Intel and all the other companies come together and they decide on a future plan for some numbers. Where do you think the on current will be for transistor? Where do you think the width and quantization number will be? Like all sorts of numbers. They decide on something. You know why? Why do they have to come? They could always hide it from each other. I'm not going to talk about this. I'm not going to give you a range at all, because they all depend on tool makers. The tools that they use to fabricate stuff that come from a different company, and they sell it to multiple companies. If Intel goes in a different direction with their numbers, they will not get anything in the market. There's no other company who will make specifically for them. Does that make sense? So all these semiconductor foundries and chip makers, they come together, they decide on some numbers, they agree upon a certain range. This is the range. And ITRS is basically something that is publicly available. You see the numbers, maybe you don't see the specifics, but you see a range. So, and these models typically match the range. That's what these models are. Okay. And this is an example of how these models could be incorporated. And I'll give you a code with these lines already in there so that you don't have to worry about it too much. Excuse me. And by the way, this is the syntax from the official command reference as to how to include an external file. All right. So I will use this slide when we discuss the DC simulation demo. I have uploaded the files. I'll open it up in a second. But before I do, let me just fast forward to the other slide. This is the second demo this is the DC demo. You'll see there will be a code about DC simulation, and we'll be using this slide to talk about the node names. And for the transient simulation, when you actually explore that at home, in your computer, look at the code, look at this circuit that we're trying to incorporate, and hopefully the names will, match with each other. Okay. Oh, by the way, the reason I also mentioned that here is because this is how you instantiate a predictive technology model. Oh, by the way, I forgot to mention the predictive technology model is for the transistor. Okay. So for example, when you simulate in Cadence, you get PDK from TSMC or some other sources, right? So that's a transistor model, essentially. You get NMOS model and PMOS model. Similar to that, you have PTM model. I don't have HSPICE model from TSMC, for example, or we don't need to for the sake of this class, but we have models from predictive technology model from ASU. So we are going to be using that. But how do you instantiate that model? You start with X, because SPICE, where anytime you incorporate anything external to SPICE environment, it treats it like a subcircuit. And any subcircuit, even when you make the subcircuit yourself, starts with X underscore whatever you want to do. 1, 2, 3, 4, give it another name. And then you have the node list. And the node list is decided upon whoever made the model. Now, when you make a model for your own transistor or any other device that you're dealing with, you choose the sequence of the node name. Can anybody answer, how can I understand the node sequence looking at a Verilog file? Do you remember in the Verilog file, there is a node list that we have to provide? After you give the module name, then you have to give a list of A, B, C. These are the external nodes. That sequence is maintained here. Whatever sequence you use in the Verilog model, you have to maintain the same sequence for the node naming. Okay. So for those people, they named it this way: drain, gate, source, body. So you have to provide this 4 name. ND is the node for drain. I'm just giving it a random name here. NG, NS, NB. This is the sequence. And after that, you have to either mention NFET, because it's an NMOS transistor, or PFET. Now, these are flexible. For example, if I were making that code, making that model for the transistor, I could have asked to provide N transistor and P transistor instead of NFET and PFET. It is basically whatever name they gave. Okay, so this is flexible based on the model maker's decision. And then this is the parameter list. Remember, I'm collaborating between Verilog and HSPICE here. I told you that in Verilog, you can define parameters and you can pass values to those parameters from other sources. Here is where I'm passing the values to the Verilog model. If I don't write this is optional. What will happen? Do you remember? Whatever was defined in the internal code of the Verilog model will be taken as the parameter. If you don't pass any parameter. And there is a default. Probably it's 1. I don't know. But if you pass something, this will override whatever was the default parameter. Okay. Similar here. Okay. And we'll see these codes. And I will not go into these slides. You have seen this before. These are just repetition to some degree. I will talk about this slide when we move on to the Monte Carlo variation analysis. Okay. So let me stop with the slides here and let me go to ensure. Let me go to the code demo. Let's bring it here. Can you see it? Okay. So when you open up, I will have to also move because I'm sharing my screen. Okay. So when you open the file I've uploaded on Canvas and unzip it, you get this entire folder. Look at this folder. Make sure to keep it within the same folder as the other codes. Only then it will run. And by the way, you have to upload it on Linux in your, ECS account, using your ECS account, any of the ESS servers. What I will do is I'll also share a video in case somebody has never accessed the ECS server, never accessed HSPICE. It will help you get started to just open HSPICE. It is not going to teach you anything else. Log into the server, open HSPICE, and just open a file. That's exactly what it will help you. I'll remember to upload that video or share that video. Maybe I'll post an announcement after I do. But assuming that you can get to the ECS server, upload these files, and just open them up and see these files. And then let's start discussing the next steps. All right. So keep this in the same folder. That's how the code is set up. If not, you can always change the code later on. So let's start with DC demo, which is the first set of file I wanted to. Oh, sorry. I want to open with text edit. All right. And the tutorial I'll upload or share, basically it is already uploaded, but I will just have to share it with you. It will show you how to run this code. This is a .sp file. You just have to type HSPICE space, just give it a file name. It will run it. As simple as that. Super simple. Okay. But for now, I mean, to save time, I'm just showing you in the text format here. Can you tell me that whether or not you can read this files? Okay, first of all, even if you cannot read it, let me see what I can do. I've never changed the font size here in text edit format and a view. Zoom in. Did you find there is a font? Format. Okay. Oh yeah, got it. Font or text.
And there's bigger.
Oh, bigger. Okay. Bigger. Got it. Thank you. Yeah, there you go. So typically you can also do it in Linux. Let's see, font, text. Where was it? Font. Okay, yeah, bigger. Okay, command plus. Okay, I'll just keep doing it. Command plus. Command plus. Okay, now it's good enough, I guess, right? I hope everybody can see it. Okay, so let's go over this code together. And after you go through one, I will show you how easy it is to move over to the second one and the third one and the fourth one. Okay, so remember, the first line is always a comment of any SPICE file. And here, we're including an external model, as you see, and it is commented out here, including the predictive technology model. And basically, in case you, when you use it for your project, I uploaded all the available models in the same folder, PTMMG. MG stands for multigate, which is the other name for FinFET. There was a time when people used to call FinFETs transistors as multi-gate transistor, but anyways. So 20 represents 20 nanometer technology. But if you change it to say 14, it will be 14 nanometer technology. If you change it to 7, it will be 7 nanometer technology. There are not other, obviously, not all the numbers are valid, as you can imagine. You cannot just make it 15, right? There is no 15 nanometer transistor technology. There is 20, there is 14, there is 10, there is 7. Okay, these are the 4 options.
These informations are given into that folder, right?
Yes, all of these are there. You don't have to worry about it. It's not, ours to change.
I'm asking the 20, 14, and 7.
Yes, this is all available in the folder that I shared. If you want to see how that looks like, let me show you. This is somebody's multi-year funded project, by the way. So somebody gave funds to Arizona State University to develop these models for many years. So it's not a trivial thing, as you can imagine. So if you go inside the model files, they have HP stands for high performance. I forgot to mention, notice I'm using HP, which is high performance transistor. If you change HP to LSTP, it will get into this folder, which is low standby power transistor. There are 2 flavors. Okay, so let's get inside HP. Notice there are like 20 nanometer, 16 nanometer, 14 nanometer, 10 nanometer, 7 nanometer. These are the models available. Okay, and you have NFET and PFET, NFET and PFET. So N and P for both. As simple as that. Okay, but we will never have to touch them unless you really want to. And by the way, I don't recommend, because if you change a parameter, you get something. That's the danger with simulation. It will show you some numbers, but they may not make sense because they are not calibrated properly. Okay, so now, assuming that you can now change the model parameters, we start with setting the options. We had a discussion about the options that SPICE provide in the last class. And I told you these options are all useful for different purposes. You may or may not need all of them. Okay, but some of them, for example, Ian told me that he was struggling with something that could be solved with this option. Like after I discussed it in the class, I don't know whether that really helped or not. But the point is, you'll realize that, oh, I'm dealing with a problem in HSPICE. How can I solve it? Even if you don't do anything, just Google it. Somebody in Reddit or something will post about it. Use this option. That's how I used to solve most problems. Now even I can ask ChatGPT, but at the time there was no ChatGPT. So Reddit or other people, like Stack Overflow, those kind of things really helped. Or sometimes if I have the time, I would go over the manual. But typically Reddit was they will point you to the option based on their real experience. Okay, so I recommend, if you don't want to change anything or do anything fancy for now, just copy and paste this section in all of your codes, because these are tried and tested. I think these are most optimized. They typically work with most simulators. So just don't do anything else. Just copy and paste it everywhere. All right. Now, next, simulation parameters. So depending on what kind of parameters you need, you create a list of parameters here, or, which I highly recommend, the more complicated the codes become, you have a huge list of parameters, right? So it's typically difficult to get to the real code if you have such a long list. So what I typically do is create a separate file, maybe .txt, maybe .sp, doesn't matter, any format, because Spice can read in different formats. And just copy and paste these parameters, cut and paste those parameters in that separate file and include that file at the beginning of the code. That way you have a separate file for parameters. Otherwise, you can just have them here. Okay. And notice what I'm trying to do here is simulate a transistor. I'm going to simulate a transistor, right? So let me show you the circuit that I'm trying to simulate here. This is the DC demo circuit. Give me a second. I hope you can see it. This is the circuit I'm trying to simulate. This is the transistor. When I simulate a transistor, I will see ID VDS and ID VGS characteristics. What happens when you change the VGS to ID? What happens when you change the VDS to ID? By the way, so that means you have to connect some voltage sources and measure some currents, okay? So you have to provide a voltage source to the gate. To avoid going back and forth, I'm going to show you here, and then when you get to the code, just try to visualize it, okay? So you see that? You have to connect a voltage source to the gate, and the voltage source will be connected between NG, which is the gate node, and ground. Ground is always 0, by the way, okay? And similarly, drain, when you provide the drain voltage, you need to have a voltage source that is connected between ND and ground. Okay. For NMOS transistors, you definitely know this. Typically, the body is connected to ground. For PMOS, it is connected to VDD, right? So this is the body terminal. You connect it to ground. And just notice one thing. I will ask you a couple of questions here. Notice, I'm just asking you to connect this body terminal to ground. But how do you connect a body terminal to ground? You can just directly make the body 0. That's one option. Okay? That's one option. But there are other options which I'll show you. That is related to the final voltage source that you see here. Notice there is a voltage source at the source terminal, but typically the source is grounded, by the way. Why am I connecting this voltage source? By the way, and also notice this is a 0-volt voltage source. So there is no voltage input here. 0-volt voltage source. So why am I connecting this voltage source here? This tells you an important factor about SPICE, HSPICE. You can measure voltages at every node. It will give you the voltages for free, even if you don't need it. Okay, but it will not give you any current. You have to specifically see current through voltage sources or resistors. That's an option, but typically I don't connect any other resistor here in this circuit. So the only thing that I can connect is a 0-volt voltage source, which doesn't change anything. It is just there. But the way SPICE is coded is, it allows you to see the current I of a voltage source flowing through that voltage source. So when I connect a 0-volt voltage source, it's as if there is nothing there. But I can then use this voltage source to see the current through that line, through that voltage source. And by the way, notice that current through that voltage source, V current, is essentially the drain current, don't you think? Drain current. So right here. Now, if I give you a code and ask you to, hey, can you also plot the body current? Meaning whatever current is flowing through the body, there is a tiny amount of current that still flows through the body, no matter how good the transistor is, okay? How can you do that? You cannot do that in current setting. But you can do something. You know what? You can insert a 0-volt voltage source and see the current through it. Are you good so far? Okay, since it is 0-volt voltage source, doesn't matter. By the way, when you define the voltage source, be mindful of the positive and negative terminal. Okay, positive terminal here is connected to ground, negative is connected to, positive terminal is connected here to gate, and negative is connected to ground. Fine, great, that's how things are. But how about this? This is a 0-volt voltage source. So you don't care where things are connected. However, depending on where things are connected, that changes the sign of the current. you get negative or positive current because there is a convention. So be mindful of the convention, and typically be mindful of the fact that negative current doesn't mean anything. It means you have just, flipped the voltage source. That's all. Okay. But if you want to be consistent, that's better to be consistent. Make sure that you always follow one rule, so that if you see a negative current somewhere, you understand the current is actually flowing in the opposite direction than the others. Okay. Always follow a convention. For me, I always consider, wherever the current enters, it's like I connect the 0 volt positive terminal there. Okay. If you can flip the other way, that's fine too. All right. So with that idea in mind, let me just go back to the code and show you how things are coded. So all I need is a bunch of voltage sources for this simple circuit, by the way. So let's start with the transistor. Can you see this line? That's where you define the transistor. I'm defining it as XN. X, basically it's a subcircuit, and then I'm just adding an extra letter here. And then the node list: drain, gate, source, and body. Are you good? Yes.
I might have missed it. Where is that transistor actually defined, like the model for that transistor?
Yeah, of course. Let me show you. So at the very beginning,
Okay,
.lib library, I'm including this transistor model.
so that makes sure that that device that you're using, the InFET,
Yes.
corresponds to that model.
Yes, exactly. But notice that it is not telling you whether it's an NFET or PFET, right?
Right.
Because it is including both.
That's both.
It is including both. And that's why you have to mention, when you define the transistor here, you have to mention that this is an NFET.
Yeah.
Notice? But in circuits, I will show you some other codes where there will be NFET and PFET both, and you can just call them out, NFET or PFET.
So what if you, and maybe this is, you don't really do this, but what if you had multiple models that you were trying to simulate together? Maybe the answer is you never do that.
First of all, your model may allow you to do so, and we always mix and match models. There are codes that I worked on where I included 3 different models for 3 different devices. But typically, the models they cannot conflict with each other. You have to make sure they don't conflict with each other. Sometimes that's a dangerous situation because some models use parameters that the other model also uses, and they conflict with each other. Okay, I ran into situations like this, so you have to handle them accordingly. You have to update the model. But for example, this one, you cannot really, based on how the PTM model is coded, if you include 20 nanometer model in the same code, you cannot do 14 nanometer model. You have to use a different code. Okay, these models cannot handle that. I don't think any model can handle it. For example, in Cadence, when you choose one model, it only gives you results for that model only. You cannot do this transistor is 20, that one is 10. No. Okay. All right. So, oh, by the way, and notice we are passing a parameter, number of fin. This is a FinFET. So, and we are defining this parameter here. Param, number of fins equals 2. By the way, I could have just set infin equal 2. That's fine too. There is a reason why we are passing a parameter within a parameter. Can anybody guess why? Because I want to vary this parameter later on. If I just set 2 here, then I cannot vary it anymore. All right. So we'll see. Then what? Then we have to connect the voltage sources. The reason I'm going slow is because this is the very first SPICE code that we're seeing together, and the next one will be super fast. The other one will be gradually faster. So let's start with the drain to source voltage. You connect it between drain node and ground, and you provide a value to the voltage source. Is it 1 volt, 5 volt, 10 volt, whatever volt it is, right? And I deliberately made it into a parameter, even if I don't need to. And I'm assigning the parameter value here, notice. Because I want to vary it if I want to later on. If I don't use a parameter, I cannot vary it. Okay, notice this is a body voltage source. And I told you the reason why we are using this 0 volt voltage source here. First of all, 0 volt voltage source, when you connect a 0 volt voltage source between NB and ground, body is essentially ground. There is nothing between body terminal and ground. It's just literally connected. So we often use 0 volt voltage sources to connect multiple nodes if you want to. But you connect, but also create the option to see the current later on. Okay, I can use this current. Okay, if I want to at some point see the body current, what I will do is I will write I of VB. Just give the name of the voltage source. Okay, I'll show you some examples going down. All right, but I have the option to see the body current. And this is the voltage source to see the drain current, as I told you. V current, remember the slide that I just showed you? Connected to the source terminal and ground, and this is 0 volt voltage source. And finally, you apply the gate voltage with a parameterized input. So does that make sense to all of you? Isn't that super simple as it gets? Just describing the circuit. Okay, any question? Now, so your circuit is established here within this section, super simple. Now it's time for you to sweep something, so change something, simulate something, right? So let's start with the reason why there are so many lines commented out is because you can pick and choose one and see the effect of that. For example, if I want to, for the way the code is set up now is we are varying the gate to source voltage. Okay, so you're changing VGS parameter going from start to stop in steps. Does that make sense, folks? So if I only run this section, and by the way, let me just comment it out here. Okay, I'm just commenting it out. Okay, if I only run this code, what it will give you is ID for different VGS. Are you good? ID for different VGS. Now, if I want to vary, I want to get ID for different VGS, which is how many of you know the name of these characteristics? ID versus VGS. What is that called? Transfer characteristics, right? ID VGS. Have you not seen ID VGS characteristics? I'm sure you have seen that. IGVGS, this is pretty standard. Okay. But now I want to see ID VGS for different number of pins. How can I do that? Super simple. Add an extra sweep like this. Sweep number of pins. Or I want to see ID VGS for different VDS. What can I do? Tell me. Just go to the top level. See, VGS, you're varying VGS here, and you're also varying VDS here. If you must have seen ID VGS for different VDS or vice versa. If you want to see ID VDS for different VGS, sweep VDS first and nest the VGS. Whatever, like play with it. Just take the code and play with it and see how the results look like. Does that make sense, folks? Okay. So it's very powerful. And here comes the alter. Notice for all of these things, I'm making start, stop, and step as parameters as well. So everything is parameterized. Okay. And notice where the stop is. The stop is at PVDD, which is like a parameter that I decided. Oh, that reminds me something. Why am I using PVDD instead of VDD? I realized that PTM model uses a parameter called VDD. So if you use another parameter, it sometimes conflicts with that model. So we're using slightly different value. So you have to be mindful of what's there. Anyways, now the point is PVDD was set as 1 volt, if you remember here in this slide. But you want to see, hey, can I use 0.7 volt in this circuit? How about 1.5 volt? How about 0.8 volt? I want to repeat the same analysis, but for different VDD. See, this is how you can do it. Dot alter and whatever parameter you change. You don't have to change just one parameter. You can change many things simultaneously. But this example shows you that you are changing just one parameter here. Okay, second example, second alter command shows you that you are varying two parameters. You are changing your VDD 0.8 and VDS to some other value, whatever. So you can keep changing the simulation environment between different alters. So when you run these simulations, can anybody tell me how many .sw0 files will be created? And by the way, let me uncomment this alter. Let me uncomment this alter so that you can give me an accurate answer. Can anybody tell me when you run this simulation, what kind of files are generated? SW. Okay, that's the, you don't have to memorize. I'm sure when you use it for a while, you will remember. But SW. Okay, sure. But how many SW files will be generated? One for the mother code, that is SW0. SW1 for the first alter, SW2 for the second alter, SW3 for the third alter. So you can easily track which file is for what condition. You can see, oh, this is my third alter condition. This is the environment for third alter. Sure, this is my third alter file. It is really nicely organized. But remember, when you simulate, first time you run simulation, you will see a bunch of files. I'm only giving you the most important files that you should care about, but there will be many other files that are generated. Most of those files will not be necessary for you. These are used for debugging and other purposes. Okay. Let me give you an example from my life. When I started using HSPICE, I was not really, that good at using it. I was trying to design an analog circuit. Those of you who work on analog design, you know how crazy it can get, specifically because most of the transistors that you care about, they need to be in saturation mode. Okay. And it is very difficult to saturate a FinFET, by the way, FinFET transistors. And I was trying to design an analog circuit with FinFET for a project. Sure. I mean, how can I know that this transistor actually reached saturation? Because it is not as simple as, VDS equals VGS minus VT, like the bulk transistors used to have. Whenever you cross that threshold, it saturates. No, it's like old story. So how do you know that this transistor is saturated? There are other conditions of saturation that FinFETs have to abide by. Turns out SPICE has a really interesting feature of assessing the modes of every transistor, and it generates a file that lists the mode of operation for every transistor. Which one is cutoff, which one is saturation, which one is linear. So literally gives you a list of X1 linear, X2 saturation, something like that. I didn't know that. So I dug deeper and used some resources and found that file, which I was ignoring from the very beginning. I never opened that file. And when I opened it, I was wow, it's like hitting gold, basically. Like, wow, look at that. So all I had to do is basically take that file and just keep running simulations until that transistor hits saturation. It was super simple. Otherwise, I couldn't even think of a good way to check for saturation in that transistor. So there is a reason why they have features. They know some people care about it. Okay. There are so many other types of files that will be generated. So don't worry about it. Oftentimes, after every simulation, people just delete all those files, because you don't want your SPICE folder to have hundreds of files with so many random names and extensions. You don't get the useful ones. Anyways, I hope that will help you at some point in the future so that you don't get surprised. Whoa, what are all these files for? You probably not need all of them right away. Okay, so that concludes our first demo for DC simulation, and we'll move over to the second one to show you how easy it is to go from one feature to the other. We'll work on top of this code. Okay, before I conclude this particular slide, this is a very important point, which is probably the number one source of error that many of you will get, is to forget to use .end. Okay, so remember, every SPICE code will have to end with .end. Okay, now I will be using a different code, which is DC demo 2, to show you some additional features. Open with text edit. Let's go. I'll be using the same trick here, common plus, 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 plus. Okay, good. All right, now everything remains the same, the exact same code, same parameter set, same circuit. Now, this is the magical portion, which is my personal favorite for SPICE, based coding. And I'll tell you the reason why. Okay. So this is the new thing of this code, and everything else is pretty much repeat of what you have seen together. Okay. We'll talk about this voltage control source, just getting ahead of ourselves. Notice we are going to do a DC simulation of VGS starting from some value, stopping at some value, and with a step. Everything else remains the same except for two things. Number one is this print, and the other one is the voltage control voltage source. Let's talk about it. Now, let me ask you a question. I told you that when you simulate in SPICE, it only gives you the node voltages of everything. Okay. And it doesn't automatically give you anything else unless you want to. Okay. If you want to see something else like a current, you have to ask for it. Okay. Oh, by the way, I forgot to mention one thing. It automatically gives you all the node voltages and all the currents flowing through the voltage sources that are connected. So you see an option on the side to click on that and see, like cadence, for example, voltage of node 1, voltage of node 2, voltage of node 7, all the voltage nodes, node voltages are available. Also, current through V1, current through VDC, current through source, whatever voltage source you have connected. That's why we deliberately connected random zero voltage sources just in case I need to see the current. Okay, so I got into the habit of connecting 0 volt voltage sources everywhere throughout my circuit. Like I had a section with like 0 volt voltage sources everywhere. Why? Because you might have to debug, right? And then I need to see the current, and then I don't have the current. So what can I do? I have to go and change my code again, which is not fun. So rather than doing so, let's start with 0 volt voltage sources from the very beginning. And every branch, if there is a branch, there will be a 0 volt voltage source in my code. Okay. All right. Now, that's very powerful because that allows you to see the current everywhere. On the other hand, what if I want to see a parameter? Because I don't see anything beyond voltage and current, but I want to see what was the parameter for that particular transistor that we are getting here. Okay. Say I want to see the number of fin for transistor number 7. You might be wondering, hey, you are passing the number of fins there. You know what is the number of fin. Okay, hold on a second. There are many hierarchies in SPICE code. Remember, there is a parameter that you're passing here. There is another parameter that is set in a Verilog code. What you haven't seen yet is sub-circuits. So oftentimes when you have small scale circuits like this, and we create a sub-circuit of them, and we use that sub-circuit in a bigger circuit, and we use that sub-circuit in another much bigger circuit. So gradually there is a hierarchy of parameters. And because of a mistake, maybe you misspelled something. Instead of, say, for example, just notice how easy it can be to mess up things. Instead of number of fins, I write number of fin. Okay. So it doesn't recognize the parameter. It doesn't pass anything, but it assumes the default parameter. You see my point here? Somehow I made a mistake, or I led to a situation where the parameter was not really passed down to the deeper level. So at some point, it will just assume the default value and run with it. How can I, specifically for debugging, oftentimes we want to see some parameters, and this is the way we do it. You can make voltage sources that are dependent, and you can set the value with any parameter you want. Anything. You can, for example, this particular transistor, voltage control voltage source, this particular voltage control voltage source is connected between test and 0. So basically, test is a dummy node. This node doesn't exist, but it is SPICE will give you the voltage at test because it gives you the voltage at all the nodes. And I'm setting the voltage at this node to be, by the way, this is how you do it. VOL equals whatever you want to set. And I'm setting it as, this is a random example for no reason, okay? You can do some maths inside, use some functions, you can calculate some things, and then set the value to be the value of test. Very good. So when I see V of test, I know it is actually a separate thing. It's not part of the circuit. It's a separate parameter that we're looking at. Maybe I want to see the current in microamps for some reason. Okay, what is the reason? You can always take the current and multiply it in MATLAB. But to make my life easy, why would I keep doing it over and over again? I will create a version of the current that is already in microamps so that it is easy for me to handle. So I gave it a name, like this is a node name, by the way, current microamps. So when I see voltage of current underscore UA, which actually the voltage at the node actually represents the current value in microampere. Are you good? And I will show you where this type of things can be very powerful moving forward. But first, see what can be done. So I take the current. This is how you find the current. Current through this voltage source, which was set to measure the current of the drain. And then you multiply 10⁶, you get the microamps current. Okay. All right. For some reason, you want to see some different value. Just do anything and set the value accordingly to that voltage source. Okay. I want to see the voltage difference between this node and that node. I want to see the, I don't know, square of a parameter. Whatever you might want to see within your code, you set it accordingly. And here is where it can become really powerful. There is another feature that SPICE provides that's called measurement. Okay. So you want to measure something. When you try to measure something, it is better to calculate few things internally and then use measure statement. I'll show you one such example where that will make sense. But for now, know that this feature is out there. if you want to see and observe some parameters or some intermediate characteristics that are not just voltage and current, okay, you can easily use as many voltage sources as you want, because none of these nodes are connected to anything else. They are all dummy nodes, okay? And you name them accordingly so that you can use these voltages to output anything. So voltage control voltage sources, they're useful for circuit context as well, but they're also equally useful when it comes to just printing random parameters out there. Okay, that brings me to the next point about how to print. If you don't use this command, it will generate files like SW0, print str0, but you can only see them using some software like Cosmoscope or Waveform Viewer. You can see them, but you don't get a text file or CSV file that you can import into a spreadsheet or or MATLAB or something like that. If you want something printed on a file, you use .print. And then this is a DC simulation, so you use DC. If it were transient, you use .print tran, okay? And then whatever set of parameters you want to print. So I'm printing the voltage at, I hope it's visible. I'm printing the voltage at node NS here, source voltage. I'm printing the voltage at this current micro. Do you know what this is printing actually? Is this actually a voltage, folks? This is actually a current, remember? Because I'm setting that value, current UA, as the microamp representation of the current, drain current. So this is essentially your drain current. So when you import, you get 3 columns in CSV format, maybe. In CSV format, by the way. And then you import it in MATLAB and just print first column, second column. MATLAB has a default function that imports from CSV in multiple columns. Super simple. And this is extremely useful when it comes to automating your work. And I told you a story from my life. I'm not showing you anything that I haven't done myself. So in Global Foundry, like, for example, they had a bunch of data every weekend. And next Monday, I was like at a loss. Like, how do I handle all of this? So I wrote a MATLAB code that used to run the HSPICE code, get all the data, automatically import them, and then plot them in different figures. And in fact, MATLAB allows you to subplot, right? They were set in a way that all the subplots are, arranged in rows and saved as JPEG. So basically, all I had to do is just open a PowerPoint, just insert those figures, and I'm ready for my presentation there. So they say, oh, wow, that many data, but actually I didn't do anything. It was working for myself while I was away enjoying myself, right? As you can imagine. So that's the power of automation. And SPICE, the reason why everybody loves SPICE is because it has so many tools that allows you to automate. Okay. All right. Now, by the way, okay, that's pretty much it. Nothing new here. Let's move on to the next demo. I hope we have time. Yeah, we have time. All right. So DC demo to transient demo. Let's talk about this now. Okay, I'll need to go back to my slide as well for this. So you have a couple of new things here in this particular demo, which will be extremely helpful. All right, let's see. First of all, for the first time ever, we're going to see NMOS and PMOS together in a circuit. And what we are implementing here is a CMOS inverter. Okay, and let me go to quickly before we talk about the slide. Sorry, talk about the code. Let me show you the slide. Can you see this again? You have NMOS and PMOS transistors. This is NMOS and PMOS transistor. The way you name them is exactly the same. You have drain, gate, source, and body. And then you mention whether it's NFET or PFET. By the way, this is the circuit we are trying to incorporate together. And you'll see when we get into the code. NMOS remains exactly how it was. You have to connect source, you have to connect gate, you have to connect the drain. Notice, by the way, before we forget, can anybody tell me where is the drain terminal of the NMOS? What is the name of the node where the drain terminal is connected? Out. So remember, in the code, when I write out, it is actually meant to show that this is a drain terminal. But can anybody tell me where the source terminal of the PMOS is? Before we forget, remember, the source terminal of an NMOS is whichever is connected to lower potential. So for example, here, NMOS's source is connected to ground. So that's why it's the source. But for PMOS, it is exactly the opposite. PMOS source is connected to the higher potential. So this node is connected to VDD, which is the higher potential. So that's why the source of PMOS is up there. So just be mindful of, that's why I've written it this way, just to remind you. This is source for NMOS, but for PMOS, it is flipped, essentially. Just so you remember, okay? All right, and then you have to connect the drain voltage as VDD, and source is grounded. PMOS body, remember, is connected to the VDD, and input and output are what we are looking at. And this is an inverter. What inverter does is inverts the input to the output, right? So we'll see how that works in a circuit setting together. Okay, let's see. We're ready for the code now. So what happened? Okay, as I told you, everything else remains the same. I typically just copy paste up to this point, up to option. Okay, and then you define whatever parameters you define. I will show you that we have a few new parameters here in a second. But okay, this is the most important part, the circuit. As simple as that. You define your NMOS, you define your PMOS, you provide all the node list. And notice, remember the list, drain, gate, source, body. So your drain for the NMOS, I just asked you the question, was out. So that's why it starts with out. What was the gate? Remember, the input was directly connected to the gate. So that's why your gate is in. Okay, source is NS and body is grounded, so 0. I don't need to see the body current, so I just directly connect it to ground. Okay, just to make my life easy. And then you mention infit and the number of in that you're sending out. Similarly, you define PMOS. All you have to do is define PFET and then number of ins. There you go. You have your CMOS inverter, 2 lines. Okay, and then by the way, don't forget that CMOS inverters typically have an output capacitor connected. If you want to connect an extra capacitance, even if you don't connect it, there will be a capacitance outside. But if you want to connect it to represent a load, you can connect. This is how you define capacitors. So I'm connecting an output capacitor to the output of the circuit, and this is the value of the capacitance. Why? Because I want to vary the output capacitance to simulate different load conditions. What if I have a higher load or lower load or something like that? So I can do that. Very good so far? Okay. By the way, this is where the capacitance value is defined. Now tell me something. How many of you remember the short circuit current of a CMOS inverter? In a CMOS inverter, NMOS and PMOS works in turn, right? When the NMOS is activated, PMOS is off. When the PMOS is activated, NMOS is off. So there shouldn't be any direct path from VDD to ground. However, nothing is ideal, as you can imagine. When NMOS starts switching and PMOS starts turning on, there will be a time when both of them will be activated simultaneously for a brief period of time. At that time, there will be a short circuit between VDD and ground. And there will be a current flowing through VDD all the way from top to the source of the NMOS down there. Are you good? That is called short circuit current. Maybe in my simulation, I want to see the short circuit current. Maybe I'm trying to plot the short circuit current. What is missing in this circuit? Can anybody tell me? Can I see any current anywhere? No, because, well, my source has to be connected to ground. It hasn't been connected to ground yet. It is connected to NS, which is not ground. How can I connect this to ground? That's why I have kept it for the voltage source here. V short circuit. We name it in a way that we understand later on that if you see the current for this voltage source, you'll get the short circuit current. Okay, and there is connected between NS and 0. That is capturing the short circuit current because that will eventually go to ground. Are you good? So when you run this code and if you plot the short circuit current, you can easily see that. Okay, now this is another new section here, by the way. This is what I typically do. Okay, if I just put in numbers like, okay, V in input 0 pulse 1, 2, 3, 4, 5, 6, 7, and 9, some numbers. I don't know what these numbers mean. Do I? I don't know what they mean. So what I typically do is I just copy and paste this section that represents what every point means. So the first 2 numbers mean the 2 voltage levels. Okay, you want to create a pulse. By the way, why am I creating a pulse? Because I want to see that 0 to VDD shift, right? When the pulse is 0, your output should be VDD. When the pulse is VDD, your output should be 0, and so on. So I'm creating a pulse to see that. Wouldn't you do that in your cadence simulation? You'll generate a pulse voltage source. So the first two voltage levels show you whether you want to go from 0 and 1 volt or -1 to 1 volt. What kind of pulse do you want? You can create that. This is very powerful. So I can set it to be 0. Notice V1 is 0, V2 is VDD. So it is going from 0 to VDD because I'm just simulating digital electronics here. I don't need negative voltage. Okay. And then TD is time delay, meaning you don't do anything to the voltage, you keep it to 0, and then after what is the delay here? 1 nanosecond, you start flipping. Yeah, I can set the delay to be 0 so that it starts simulating from the very beginning. You have the option, you may not need it. And then rise time and fall time. Remember, rise time is how long it takes to get to VDD, fall time is how long it takes to come down. You have control over that as well. And active time is how long it stays at VDD. And the time period is total time period with VDD and 0, one full cycle. So you have full control over the shape of the pulse. So this is very powerful. You can shape any pulse you want, exactly like what Cadence does. You have all these options in Cadence as well, except here, when you write code, you can vary anything. You can keep sweeping them the way you want to using single line of code. Okay, so now I've provided this input to the circuit and I will do a transient simulation. Here is how you do a transient simulation. Dot tran, obviously, this is first you mentioned the step size. Okay, what is my step size? 10 nanosecond. Sure, you can also do 1 picosecond if you want to. Okay, my understanding is as of now it only supports up to 1 picosecond. I have never seen anything less than that. Okay, all right, so 10 nano, that's my step size. Stop at, sorry, 10 pico is the step size, and stop at 10 nano. And then, by the way, this is enough. This is enough to run the transient simulation. It runs the transient simulation, and when you open up with waveform viewer, you see the input and output. Just click on V in, you get to see the pulse. Click on V out, you get to see the opposite pulse. That's how your circuit works. Okay. Now I want to see the effect of capacitance on top of these characteristics. I want to see them nested on top of each other. Sure, just add an extra nested sweep. That's when, just to illustrate that you can, keep varying parameters within the transient simulation. Go from 10 femto to 50 femto. Great. Do that. And by the way, similar to the DC simulation, you can use alter for transient as well. Nothing changes. Okay, instead of 1 volt, I'm changing VD to 0.7 volt. Nothing special about this condition. I'm just showing you that you can do it. You can nest alters within transient or DC simulation. So, are you good so far? Finally, last but not least, I will reuse this code again to show you the very last demo with transient subcircuit. I want you to try this out at home. Only then you understand, only then you can really see whether you understood it properly or not. Okay, command plus. Okay, see, everything else is same. I want to illustrate two things. Number one, where are the parameters? They're gone. What I did was I just cut, paste them in a separate file. I created a file called get_params.inc, just text file, and then pasted them out there. And I'm incorporating them using include. I recommend doing that. Okay, don't use the parameters here. Looks messy. The code looks messy. All right, so it's much cleaner. Now they're there. All the parameters are there, but in a different file. Okay, this is the most powerful thing in SPICE. This is what makes SPICE so useful for industry, because you can keep making subcircuits and keep making them bigger. Subcircuits within subcircuits within subcircuits. Okay, nesting subcircuits. So remember the inverter that we just developed? Can you recognize this code, folks? XPXN. Can you recognize this? So I'm just trying to make that inverter again. But instead of just making the inverter, I'm trying to see it like a symbol. Imagine if it is a black box, what are the output pins and input pins you need? You need an input for the inverter, don't you think? You need an input. You need an output of the inverter. You need to provide a VDD. So this is my input node. If I want, I can also create a ground node, NS. But I don't want. I'm not gonna deal with ground. Just ground it internally. Okay. So then when you code PMOS and NMOS, use these exact node names. input, output, NDD. Notice I've never attached VDD here, have I? I've never attached VDD. Why? Because I'll be doing it when I actually call this subcircuit. It is like a symbol. You have the pin to connect VDD, but you don't connect VDD in the subcircuit. Are we all together or no? Don't give up. If you have questions, let me know. Okay, so for now, I don't have any voltage sources anywhere in the circuit because I'm leaving it for later. This is like a symbol with input and output pin and VDD pin. So you have input, output, and VDD. All of these are nested in the circuit connection. Also notice, I'm keeping this option to provide a parameter, number of pin. And this is where I told you that you might miss some nesting parameter. To provide this parameter internally, you need to make sure that also have this line in the sub-circuit definition here. If you don't have this line here in the first sub-circuit definition, then it will always keep taking the default values. And we all made that mistake when I started coding, by the way. Like I didn't realize that you also have to mention it here in the sub-circuit definition line. Otherwise, it will not let you change it. Okay, it will just take the default value and move forward with it. Okay, this is how you define sub-circuit. After you make the circuit, everything else remains the same. You start and give it a name. Dot sub-circuit, give it a name, inverter stage. I'm just deciding to give it name. And then end sub-circuit, end S. Okay, that's your sub-circuit. Okay, and let me show you how to use that sub-circuit. Okay, I think I can just make it a little bit longer. Okay, no, I thought it, oh yeah, there you go. Notice, I am doing a 5 inverter chain. Give me like 30 seconds, okay? I just want to finish this. X inverter 1. You need input, output, what else? What else? VDD. Input is N1, output is N2. This is my VDD. I'm just giving it a name, VDD input. Are you good? Where can I give VDD input? Notice, this VDD is connected here. I've also already connected a voltage source at the VDD input. So it is getting VDD, is it not? Okay, second inverter. So the output of, just visualize this without any drawing. You have 5 inverters driving each other. So the output of the first one is the input of the second one, right? So notice, this is the input. N2 was the output of the first one. So now it's the input and the output is N3. For the next one, it's N3, N4, then N4, N5, then N5, N1. What does that tell you? The output of the last one is fed back to the first one. What is this circuit? This is a ring oscillator. 5 inverter ring oscillator. If I want to convert it to a chain of 5 inverter, what do? Okay, N1 and just make it N6. Done. It's no longer a ring oscillator. It's a chain of inverter. Does that make sense? Okay, I typically can easily ask this question. Okay, make it a 7-stage ring oscillator. How can I do it? Just, okay, copy this to 7-stage, right? So let me show you. Sorry, it's because of zooming in, it has become unstable. Okay, 5, just to show you the power of coding, 6, 7, okay? So from N6 to N7, and N7 to what? N1, because this is a ring oscillator now. Done. There you go. Everything else remains the same. That's the power of subcircuits, okay? And this is just a simple example. And there you go. You can easily do it. So that's the last message I want. Everything else remains the same. Nothing else changes, okay? That is the message I wanted to leave you with. So that completes our HSPICE demo. Please try out these codes and, let's discuss next. Thank you. Take care.
You have